Well, so far we talked about topological spaces and we went over some examples. Today, we're going to talk about the basis for a topological space. A basis is a collection of subsets of X that help us to describe the topological space. Let us go over the definition together. Basis for a topological space. So let X be a set, a basis for a topology on X, which is denoted by beta, is a collection of subsets of set X such that that collection satisfies the following conditions. Every element in set X belongs to a member of beta. For every member in X, we can find at least one basis element like B such that X belongs to B. Well, the second condition, if a member of X belongs to two basis elements, B1 and B2, for sure you can find the third basis element like B sub 3, including X, and it is included in the intersection of B1 and B2. So if X belongs to B1 and X belongs to B2, B1 and B2 are basis elements. So B1 and B2, both of them are members of beta. Then there is a basis element like B3. So note that B3 belongs to beta such that X belongs to B3 and B3 is a subset of B1 intersection B2. So this is the definition of a basis for a topological space. Now, what if we have a collection of subsets of X that satisfy these two conditions? How do we define a topology using that basis? So let beta be a basis. The topology related to this basis is called the topology generated by the basis beta. The topology generated by beta is defined as follow. Now remember that in previous lecture, we talked about the elements of a topology and we call them open sets. So U as a subset of X is an open set. It means that U belongs to a topology if for any X in U, you can find a basis element in beta, including X, and it is included in U. For any X in X, if X belongs to U, we can find a basis element B belongs to beta such that this basis element includes X and it is included in U. The topology generated by beta is defined as follow. Later on, we're going to see this topology is indeed satisfies those three conditions that we use to define a topological space. Short recall. Let X be a set, a topology on X, like tau, is a collection of subsets of X such that, first of all, empty set on X belongs to tau. Tau is closed under union, and 3, tau is closed under finite intersection. Remember that for this new object, mathematical object that we define here, its elements are called open sets. U belongs to tau is called an open set. So when we're talking about the topology generated by beta, we are talking about the elements in tau, like U. We say that U is an open set if U includes X, then for sure you can find a basis element like B such that X belongs to B and it's included in U. So U in this case is an open set. Very well. So let's show that this is indeed a topology on X. Topology tau generated by beta is indeed a topology. So we need to check these three conditions. Also remember the definition of a topology generated by basis B. U belongs to tau if X belongs to U. You can find a basis element like B such that X is in B and it's included in U. Very well. So we're going to show that for empty set and for X itself. So this is our goal, to show that empty set or U belongs to tau. If X belongs to empty set, we can find a basis element like B such that X belongs to the basis element and it's a subset of empty set, which is true vacuously. Now, our goal is to show that X or U belongs to this topology. So let us follow the definition. U belongs to topology. What's the meaning of that? It means that if X belongs to U, which in this case is X, we can find a basis element B such that X is in the basis element and it's a subset of X. This is also true. Why is that? Remember the definition of a basis, number one. So it is true by the definition of a basis. This is number one. So we proved number one, empty set and set X, both of them are members of this topology. Now we're going to show that this topology is closed under union. Two. This is our goal. To show that this topology generated by this basis, which our goal is to show that it's actually indeed a topology, is closed under union. Well, how do we show that? Remember that our goal is to work with the elements in that topology. So suppose you have a collection of open sets in your topology. You want to show that if you take the union of these elements, the union belongs to tau. What's the meaning of that? It means that if X belongs to U, U is the union of these elements, these sets, then we can find a basis element such that X belongs to the basis element and it's a subset of U or the union of U sub alphas. We want to show that if X belongs to U, what is U in this case? U is the union of these open sets. We can find a basis element like B such that X is in B is a subset of U, or which is the union of U sub alphas. This is our goal. Very well. So X belongs to this union. Since X belongs to the union of U alphas, it means that it needs to be a member of at least one of these elements, one of these sets. So there is an index like alpha such that X belongs to U sub alpha. So recall that U sub alpha belongs to the topology. We already know that U sub alpha is an open set. We already know that U is an open set. Since U sub alpha is an open set, or in the parentheses U sub alpha belongs to the topology, it means that we can find a basis element like B such that X belongs to B and B is a subset of U sub alpha. Well, X belongs to B, B is a subset of U sub alpha. It means that B is a subset of the union as well. By the definition of union, X belongs to B, B is a subset of U sub alpha, which is a subset of the union of U sub alphas, which is nothing but U. So it is true. So we just showed that our topology, which is generated by the basis, is closed under the union. What's left is to show that this topology is also closed under finite intersection. That's how we are checking that it's indeed a topology. Is to show that so is closed under the finite intersection. So let us use induction to prove this. Let U1 and U2 be two open sets in our topology. Our goal is to show that U1 intersection U2 is also a member of TO. We'll show that U1 intersection U2 is in TO. Okay, so following the definition of a topology generated by a basis, we need to show that their intersection has X, then we can find a basis element like B such that X is in B and it's a subset of the intersection. It means that we need to show that if X belongs to U, which is the intersection between U1 and U2, we can find B, a basis element, such that x belongs to B is a subset of U1 intersection U2, which is our U. There you go. So let us take a look at this. X belongs to U1 and U2. Using the definition of intersection, it means that X belongs to U1 and X belongs to U2. These two are open sets in our topology. What's the meaning of that? It means that since X belongs to U1, there is a basis element B1 in the basis such that X belongs to B1 and it's included in U1. Also, U2 is an open set in our topology, so we can find another basis element like B2 such that X belongs to B2 which is a subset of U2. Well, what's the meaning of that? It means that X belongs to B1 and B2, which is a subset of X belongs to B1 intersection B2. By using the definition of a basis, we can find a basis element B3 such that X belongs to B3, which is a subset of B1 intersection B2, and this intersection is a subset of U1 intersection U2. This is the base step of our induction. Well, now suppose we want to show that for U1, U2, U3, UN intersection. So let U1 intersection U2 intersection UN minus 1 belongs to 2. What's the meaning of that? It means that if X belongs to the intersection of U1, U2 to UN minus 1, we can find a basis element like B such that X belongs to that basis element B and it's a subset of this intersection. We want to show that U1 intersection U2 intersection UN is also a member of our topology. So it means that if X belongs to this intersection, we can find a basis element like B such that X is in B and it's included in the intersection U1, U2, UN. Well, by the hypothesis that we have, U1, U2, UN minus 1 belongs to 2. We can just call this like V. And also UN belongs to 2. It's similar to what we did as the very first step, base step in our induction. both are open sets, we can find basis elements like B1 and B2 such that X belongs to B1, subset of B, and X belongs to B2, subset of UN. Following the definitions. Well, now it's the same as before. X belongs to B3, which is a subset of B1, intersection B2, subset of V, intersection UN. So X belongs to B3, which is a subset of U1, intersection U2, intersection UN. So we're done with the third one. It means that we just show that topology generated by a basis is indeed a topology. A couple of examples. So we are going back to previous lecture examples, the circular regions. Let beta be the collection of all circular regions. So when we're talking about circular regions, we're not talking about disks. We're talking about the interior of those circular shapes. So interior. Then this collection is a basis. We can check two conditions for this basis. The very first one, if you remember, for any X in the space, we can find a basis element such that X belongs to that basis element. Very well, so our space here is the plane. We are working with circular regions in the plane. So for plane, if we take elements in the plane, we can definitely find circular regions including those elements. For the second condition, if X belongs to B1 and B2, both of them are basis elements, then we can find the third basis element like B sub 3 in the basis such that X belongs to B3 and it's included in the intersection of B1 and B2. Okay, suppose X belongs to B1 and also X belongs to B2. So of course we can find B3, which is a subset of the intersection of B1 and B2. example that we have is B to be the collection of rectangular regions, and we can just show that it forms a basis for space X. So let B prime, beta prime be the collection of all rectangular regions again, we're not including the boundaries, just the interior of the rectangular regions. Then beta prime is a basis, and it satisfies the conditions that we have for a basis. The very first one, for any x in the plane, we can definitely find a rectangular region including that x. Also, if x belongs to two rectangular regions, then we can find a third rectangular region such that x belongs to B sub 3 and it's a subset of B1 intersection B2. So if we have a rectangular region and x belongs to it, and there is another rectangular region. So this is B1 and B2. We can find the third rectangular region, B sub 3. Another example for you. Recall discrete topology, which is the collection of all subsets of X. We can define a basis for the discrete topology. So let X be a set tau equals to P of X, the power set of X, which is the collection of all subsets of X is called the discrete topology on X. The basis for discrete topology is the collection of all one-point subsets of X. We can define a basis for this topology, which is the collection of all one-point subsets of X. For example, if X is the set including A, B, C, remember that the topology over it, the discrete topology over it, is defined as the power set of X, which is including empty set, X itself, 1 point subsets, 2 points subsets, and B and C. This is our topology. The basis for this topology is going to be the set including set A, set including set B, and set including C. As you can see, the cardinality of the basis element is the same as the cardinality of set X.